This example is going to exemplify how we can find definite integrals using a variable substitution, but that we have to be careful about the ends of our integrals, so the bounds of the integral. All right, let's work on solving the integral from 0 to 1 of 2x times 7x squared minus 3. So this tells me that x is traveling from 0 to 1. All right, so you could integrate this without a variable substitution, but let's use a variable substitution. You want to choose your variable to be the object that has a derivative present. So let's choose the 7x squared minus 3 because that's going to differentiate to something that just has an x. Right? du is 14x dx. Now you're looking for a 2x dx. So you can divide both sides by 7 and you get your 2x dx. So this is equal to the integral. The 2x dx is replaced with 1/7 du. So the 2x and the dx have been taken care of. Now you just have that parentheses, which is u. So we have 1/7. Oh, wait. Before we move on, where are my bounds of integration? So over here, this integral tells me that I want to find the area underneath that curve, that function, as x travels from 0 to 1. But what does that mean about u? So let's take that definition there. U is equal to 7x squared minus 3. And if x is starting at 0, what is that going to mean about u? So if x is equal to 0, then that means u is equal to 0 squared is 0, 7 times 0 is 0, 0 minus 3 is minus 3. U starts at minus 3. All right, where's u going to end up? So x ends its journey at 1. So when x is equal to 1, and you plug a 1 in, 1 squared is 1, 7 times 1 is 7, minus 3 gives you a 4. So u travels from minus 3 to 4. Okay, let's integrate this. This will be 7 times 2 is 14, u squared, evaluated between minus 3 and 4. All right, let's see. If you plug in a 4 there, you get a 16 over 14. If you plug in a minus 3, you get a 9 over 14. 16 minus 9, what's that going to give us? A 7. We get a 1/2. Okay. So let's solve this again, except remember how we had to find our new bounds of integration once we moved variables? Well, you don't actually have to do that, but it's still equally as complicated. Let's revisit. We can write this integral as the integral of u times 1/7 du, right? After we employ the variable substitution, this is what we get. And at this stage, last time we figured out what these bounds were, but now I'm just going to leave them as variables and I'm going to ignore them. I'm going to perform my integral. So that is 1/14 u squared, evaluated between first question mark and 2 question marks. And now, as long as I take it back to x, I can use the bounds for x. Right, now this depends on x, and x was traveling from 0 to 1. So just make sure that the bounds agree with the variable that you're using. If you did a variable substitution, then make sure that you have the correct bounds, or you can ignore the bounds for the moment. Just make sure that you have variables as placeholders. And then once you get it back to your original variable, you can use your original variable's bounds. Let's show ourselves that we do, in fact, get the same thing. If I evaluate this antiderivative at 1, 1 squared is 1, times 7 is 7, 7 minus 3 is 4, 4 squared is 16. So I get a 16 over 14. Yeah, it's the same thing so far. Minus, if I evaluate that antiderivative when x is equal to 0, I get 0 squared is 0, times 7 is 0, minus 3 is minus 3, minus 3 squared is 9, 9 14ths. Yeah, everything's the same. Right. So the moral of the story is you can either find your new bounds and use your new variable, or you don't have to find your new bounds, but just remember to make sure to go back to your original variable at the end.